Okay, for this screencast, we're going to do something called forward differencing. Backward differencing, midpoint differencing, second order differencing, they all go around the same principle. I'm going to do a clear CLC equals all. Let's do sine of x. I'm going to say x is minus pi to pi. I'm going to say y equals sine of x. I'm going to do fig equals figure, set fig, comma, color, comma, white. Plot x comma y, line width comma 2, x label x, y label y. Okay, there's my sine function. Throw a grid on, and we're ready to go. Okay, and then what I'm going to do is I'm going to copy and paste this. So Control C, Control V. And I'm going to do y deriv. And y deriv is equal to what? Well, it's equal to the cosine of x. So then here's my cosine of x function. Okay, so now what I want to do is I want to use forward differencing to compute the value of y deriv numerically. Now, up here, x equals pi 0.1 to pi, I actually want to call this del x, and that way I can change that. So del x is 0.1. And I'm actually going to make it 1 for now. So if I look at my cosine function, it's pretty bad, but I'm going to use that just for now just so you can see. So the equation for forward differencing is here. F prime of x is approximately equal to f of x plus I minus f of xi divided by delta x. It's all right here. So what I'm going to do is I'm going to say my y deriv estimate is equal to my function y, and now I need to start at 2 and go to end, and then subtract starting at 1 going to n minus 1, and divide that by del x. And then now I can hold on and I can plot. And this is where things get interesting, right? This is 2 to end, and this is 1 to n minus 1. So actually, I can only plot x from 1 to n minus 1, comma, y deriv estimate in red. I'm going to do a line width of 2. I'm going to throw a legend down. This is actual derivative, or let's say analytical derivative. And this is numerical derivative. Okay, and there we go. So if you look, the difference between the analytical and numerical derivatives are terrible. So what you want to do is make your del x smaller. So if you make it say 0.5, now we're getting somewhere. It's getting pretty good, and it looks like I'm actually shifted. So let's make this 0.1. Again, I'm still shifted by a little bit. So what I want to do is I want to actually do 2 to end, rather than the other way around. And it looks like it doesn't matter. It's shifted by a little bit. Maybe we can do minus del x or something like that. Let's do minus del x over 2. There we go. Okay, so now we've got a del x of 0.1. I shifted over the derivative by a little bit, and I match up pretty well. Again, if I do, say, a del x of 1, my function doesn't match up that well. You can see there's a lot of differences between my analytical and my numerical. And that's it. If you want to do any of the other ones, like f double prime or f prime, this is backward differencing here, and this is midpoint differencing, or if you want to do a second order differencing, they all operate on the same way of, y of 2 to the end minus y of 1 to the end over del x. And that's it. Good luck.